Assalamualaikum and a very good day to our lecturer. Today our group is here to present our group assignment project. Before we begin our presentation, I would like to let my group members introduce themselves. Hi, my name is Nur Amira binti Sahir and my number matrix is B122510595.
Hi, my name is Shazwa Alisa binti Shaiful and my matrix number is B122510666.
Hi, Assalamualaikum. My name is Wan Nurina Akila. My matrix number is B122510608.
Hi, my name is Nur Rafika Aisha binti Ahmad and my matrix number is B122510656.
For this presentation, I will be starting off by covering the first phase of our project. That's one, which is convolution of a one-dimensional signal.
Let's look directly at the core implementation logic in our code. Firstly, we use audio read to import our raw audio recording. Then we check if our recording is in stereo. If it is, we arrange the channels into a single monocolumn because one deconvolution slightly requires a single channel signal. Next, we convert our physical 0.3 second delay into a digital sample index by multiplying the time by our sampling frequency. This part we build our impulse response H. We set a gain of 1.0 at time 0 for the immediate direct sound and a scale gain of 0.4 down the timeline to represent the reflected echo at 40% volume. This is the most important line. We perform discrete linear convolution to mathematically pass our clean voice through our ecosystem to synthesize our final output Y. For playback, we use sounds as C because it automatically normalizes the amplitude to prevent speaker clipping. And we use calculated pause intervals so the track don't clash and overlap. Now let's run the code to see the output.
I am Nurul Rafika Aisha binti Ahmad.
I am Shazwa Alisa binti Shaiful.
I am Wan Nurina Akila binti Y Muhammad Fazirat.
I am Nur Amira binti Sahir.
I am Nurul Rafika Aisha binti Ahmad.
I am Shazwa Alisa binti Shaiful.
I am Wan Nurina Akila binti Y Muhammad Fazirat.
I am Nur Amira binti Sahir.
So looking at our generated plots, we can visually confirm the success of our convolution mapping. The top plot shows our clean raw input voice signal spanning about 16 seconds. And the middle plot is our system blueprint. It displays our direct sound at time 0 with a gain of 1 and our echo spike exactly at 0.3 second with a scale gain of 0.4. And lastly, the bottom plot is our convolve output. Visually, the waveform is slightly elongated and looks denser because our discrete convolution has successfully overlaid every single audio sample with its own 0.3 second reflection.
I am Rafika Aisha binti Ahmad.
I am Shazwa Alisa binti Shaiful.
So next, look at the fourth task 2. So we develop a melody synthesis system using the principle of the Fourier series. Instead of producing just a single, flat, monotone, so we manipulated three primary harmonic, which is the first is a fundamental frequency, F0, and the second harmonic and the third harmonic. So we use three harmonic to generate a more realistic instrument timbre. So I choose a 10-second happy birthday song. In the MATLAB code, we utilize anonymous function to efficiently build the Fourier series synthesis formula, which is signal time equal to amplitude 1 multiplied with sine 2 pi f0 t plus amplitude 2 sine multiplied with 2 pi 2 f0 t and plus amplitude 3 sine multiplied with 2 pi 3 f0 t. So this formula combine the amplitude 1, I use 10 for fundamental frequency f0 and for the amplitude 2, I use 4 for the second harmonic that provide dip, and the last amplitude 3, I use 1.5 for third harmonic to add brightness. So this decline amplitude sequence mimic real world physics, where harmonic energy naturally dissipates at higher frequencies. I also put the T-long and T-short at the MATLAB code for vectorized time and rhythm. So the for T-long allocated for the whole musical phrases and also for the T-short allocated for quick standard structural syllables. Uses a functional single line anonymous function, also can handle long and short to compute full three harmonic Fourier for any given pitch. The next individual phrase array, which is a P1 to P4 function for single concatenation into single master matrix to complete 10-second song structure. So, for the result analysis, the simulation result are shown in this graph. So we use a very precise time window of 0.015 second to verify that each harmonic vibrate at the correct frequency, multiply exactly 1 time, 2 time, and 3 time the fundamental frequency. So this serves as a visual proof that the Fourier series act as a building block for every musical note we synthesize. Finally, each note was arranged using different time vector to create the rhythm for Happy Birthday. So I used the sound function to transform this digital data into analog signal using digital to analog conversion. So let's listen the result simulation using MATLAB.
We explain about task 3, which is fast Fourier transform. The objective of this task is to convert an image from spatial domain into frequency domain, and also reconstructed back the image by using inverse fast Fourier transform. Okay. Firstly, I capture a photo of my team members that used as original image. The image was imported into MATLAB by using IMRIT function and shown in figure 1. The image was converted into grayscale by this RGB2 function and shown as figure 2. Next, I apply the FFT2 function to transform the image into the frequency domain. I use FFT shift function to make the frequency spectrum easier to visualize, and shown in figure 4. And in figure 5, I apply log transform to enhance the visibility of frequency magnitude. Lastly, I use FFT2 function to perform inverse fast Fourier transform, and the image will be reconstructed back. And the figure 6 is the image. As shown in the result, this is the original image, figure 1, figure 2 for gray image, figure 3 for Fourier transform of an image, figure 4 center Fourier transform of image, figure 5 log transform, and lastly reconstructed image. The reconstructed image is identical with original image, which show that fast Fourier transform and inverse fast Fourier transform process are successfully performed with minimal loss. In conclusion, the fast Fourier transform is an effective method for analyze image information in the frequency domain, while the inverse fast Fourier transform allow image to accurately reconstructed back into the original form. That's all from me.
Moving on task 4, let's look at the actual function of our MATLAB code. First, as pointed out by the top arrow, line 4 uses the IMRIT function. This reads the specific JPEG image file directly from the computer's directory and stores it as a data matrix inside the variable I. Next, the bottom arrow focuses on line 5 through 8, where we use IMGauss field. This critical function applies a Gaussian low-pass filter to smooth out the image, effectively creating a blur effect. Notice how we vary the second parameter, which is sigma, as the value of sigma increases from 2 up to 19. More high frequency details and noise are removed, making each subsequent image look progressively blurry. Demonstrate how this MATLAB script applies Gaussian low-pass filtering. As I click the Run section button, the code executes instantly. And a figure window pops up with multiple tabs, displaying our results side by side. Looking at the figure 1, this is our sharp, unaltered original image of 4 people standing outdoors. And then in figure 2, we apply a mild filter with a sigma of 2, making the image slightly softer. Next, figure 3 uses a sigma of 5, introducing a moderate blur that smooths out finer details. In figure 4, with a sigma of 10, the facial features and backgrounds become heavily obscured. And then lastly, figure 5 shows our maximum sigma of 19, where almost all details are stripped away. This clearly demonstrates how a higher sigma increases the blur intensity in MATLAB. Okay.